Thank you very much. So it's nice to be here in Beijing. I see so many familiar and unfamiliar faces in the audience. And I'm giving this talk on behalf of joint work with Josh Green. And the starting point for this work appears on this board. It's a Toeplitz square peg conjecture dating from 1911, which is still unsolved in the generality in which it's stated on this board. So that says for every Jordan curve gamma, and gamma is going to remain my notation for Jordan curves throughout the talk. It's just a subset of the plane that's homomorphic to the circle. There exist 4 points on gamma at the vertices of that square. And so here I've got a picture of a Jordan curve. It's not just a scribble. And if you look carefully enough, you should be able to find a square which has all 4 vertices lying on the Jordan curve. So in particular, we don't want the square to lie inside the region bounded by the Jordan curve. It's just 4 vertices got to lie on the Jordan curve. That's what the Toeplitz square peg conjecture says. And as I say, it's as yet unsolved. It's also perhaps a little bit undermotivated, just as stated. Why would you ask this question? So let me tell you a couple of things. So first of all, if I can continue writing on this board, so you can find triangles. Let's say you can find the vertices of a triangle of any given similarity class on any given gamma. So if you were to make the Toeplitz triangle conjecture, there's the answer. If you've got your favorite triangle, you can always find 3 vertices in any given Jordan curve that form that triangle. So this question is not interesting for triangles. It's also not interesting for pentagons. So 2 dissimilar, let's say, the vertices of 2 dissimilar pentagons never lie on the same. I'm going to make a full statement, so maybe I shall erase it before I reach the end of it. Let's try again. So 2 dissimilar ellipses. That is, ellipses of different eccentricities never inscribe pair of similar pentagons. So, in other words, if you give me vertex set of a pentagon, then there's going to be at most 1 similarity class of ellipse that you can find the vertices of that pentagon on. I've used the word inscribe there, trying to drip that in slowly. I'll give you a formal definition of what I mean by inscribe in a second, but it's probably what you think it is. So the first result towards the Toeplitz square peg conjecture is by Schnirelmann in 1929. Well, before I say that, maybe let me say, in case it wasn't obvious, that The square peg conjecture, when phrased for triangles or even triangles, is boring because you can always find vertices of triangles in any given Jordan curve. It's boring for pentagons because things don't work even when the Jordan curves are just ellipses. So it's more interesting to ask it about quadrilaterals. And a square is just the first quadrilateral that you think of. So that's why you make that conjecture about squares. And the first work on it, Schnirelmann, 1929, proved that the Toeplitz square peg conjecture is true whenever your Jordan curve is smooth. That's essentially a Bordism argument. You imagine starting with an ellipse which inscribes exactly one square and deforming your ellipse through smooth Jordan curves till you arrive at the smooth Jordan curve that you're interested in. And you see, as you do that, pairs of inscribed squares will blink in and out of existence, but they'll blink in and out of existence in pairs. So the number of inscribed squares generically is 1 modulo 2, in particular is non-zero. Roughly speaking, that's how Schnirelmann's argument goes. So the game is, or a game is, to try to weaken smoothness. And most of this talk is going to be trying to follow this arrow, starting with Schnirelmann's theorem, if you like, and trying to see how far we can weaken down that condition on gamma to see how close we can get to the Toeplitz square peg conjecture. However, there's something else you could try, which is to weaken squareness. So not to triangles. Triangles are boring, but maybe to other quadrilaterals. So here I'm going to quote a couple of theorems. So theorem. This is to Green and myself back in 2020, in the throes of the pandemic. So any similarity class of, leave a gap there, quadrilateral inscribes, underline that word, in every smooth Jordan curve gamma. Okay, so minus one very important adjective. That's a result that we proved in 2020, so I'm going to fill in that adjective in a second. I'm underlining the word inscribes because I'd like to give you a definition of it. So here's the definition of inscribes. So given a Q inside C, Q is going to be the vertex set of some quadrilateral. It's going to consist of 4 points. There exists a PZ. This is a linear polynomial in Z with complex coefficients A and B, A non-zero. Such that P of Q is contained in gamma. So this is Q inscribes in gamma. this is the definition of what it means for a quadrilateral, its vertex set, to inscribe in a Jordan curve gamma. So what's going on here? Well, if you think about this vertex set Q and what multiplying that by A does, well, A is just a non-zero complex number. Think of it as having two parts. One is its argument, which might rotate that quadrilateral by theta. And the other part is its magnitude, which might scale that quadrilateral. So you're allowed to rotate and scale your quadrilaterals. And then B is a shift. So you start with your quadrilateral, you're allowed to rotate it, enlarge it, shrink it, and then with some shift, you can sit it on the Jordan curve. So that's what it means for this quadrilateral to inscribe on gamma. There's a theorem we proved last year. Well, maybe I should tell you before I go on what the correct statement of this theorem is. So there's a missing adjective here, I said, comes just before quadrilateral. And the adjective comes by thinking about the smooth Jordan curve, the circle. So if you want to think about a point set Q that inscribes in every smooth Jordan curve, then it had better be a point set that inscribes in the circle, because the circle is sort of archetypal example of a smooth Jordan curve. So the only quadrilaterals which this could possibly be true are the cyclic quadrilaterals. Any similarity class of cyclic quadrilateral. And that just means Q is a subset of the unit circle, if you like. All right. So this is, in fact, the most general theorem you could hope to prove, because if you've got a quadrilateral that inscribes in every smooth Jordan curve, it has to inscribe in a circle, so it must be cyclic. It's also optimal from another point of view. You can't just drop this smoothness hypothesis and have this theorem remain true. So note, not every cyclic quadrilateral inscribes in every triangle. So here the triangle is playing the role of the Jordan curve. A triangle is a nice Jordan curve, but it's not smooth because it's got these three corners. And it's in fact not true that every cyclic quadrilateral inscribes in every triangle. So you need some sort of regularity hypothesis on the Jordan curves to make that theorem true. Here's a generalization of that theorem, or maybe it's not strictly a generalization. So this is from 2024. So if Q is a subset of S1, Q has 6 points now, then there exists a quadrilateral in Z, a quadratic in Z, AZ squared plus BZ plus C, that's not constant. So AB is not equal to 0. And I guess I need a smooth gamma. Such that P of Q contained in gamma. Okay, so Q up here stood for quadrilateral. Q down here stands for questionable choice of notation, perhaps. But this is a cyclic hexagon. And what this theorem says is that you can't linearly inscribe necessarily a cyclic hexagon into every smooth Jordan curve, but you can do so quadratically if you allow yourself to go to a quadratic. Okay. So let me tell you the ingredients of these two theorems. Or the major ingredients. So the ingredient of the first theorem, coming from symplectic topology, is a result due to Polterovich and Viterbo independently. Which says that embedded Lagrangian tori in C2 have minimal Maslov number 2. Okay. So that turns out to be the ingredient for the first theorem. I'll say more about how this ingredient crops up as we go through the talk. The ingredient for the second theorem is more recent, though it's in the same vein. And this is a result due to Fukaya and Irie. I need a comma. This says that an embedded Lagrangian genus 2 surface times S1 inside C3, so we're going up the dimensions here. We're looking at Lagrangian inside C3 now, has point times S1 with Maslov index 2. So both of these theorems come down to questions about when you can embed Lagrangians or what properties embedded Lagrangians have inside Cn. If you've mistakenly wandered into this symplectic topology seminar and you don't know what a Maslov index is or a Lagrangian, bad luck. But let me tell you, so Lagrangian is a special kind of smooth submanifold. Each tangent plane at a point lies within a particular subset of allowable tangent planes called Lagrangians. And so as you travel around a loop on your embedded submanifold, your embedded Lagrangian, you get a loop in the space of Lagrangian 2 planes. And that gives you a winding number in that space of Lagrangian 2 planes, it turns out. That's called the Maslov index. This is Maslov index 2, this loop. Minimum Maslov number is you just look at all the positive Maslov indices of all the loops, and if the minimum number that you see is 2, you say it's minimum Maslov number 2. So that's what's going on. So these are sort of winding numbers. Now, how this talk is going to go is, like I said, I'm going to be following this arrow. I'm going to be trying to weaken smoothness rather than weaken squareness. But what I'm going to do is, as I sort of give those geometric constructions related to that arrow on the right, I'll point out where this embedded Lagrangian torus comes from. So we'll see that in a second. All right, so any questions so far? Brilliant. Okay, good. Let me make some space then. Awesome. All right. So we're going to think about weakening smoothness, and our starting point is going to be Schnirelmann's theorem. So given a general gamma, one thing you can do is to try and approximate it by a sequence of smooth Jordan curves that gets closer and closer to the Jordan curve that you're interested in. So that's the general idea. So given a general gamma with no smoothness constraints, we approximate by a sequence gamma n, which converges to gamma, some suitable sense, where each gamma n is smooth. Now, Schnirelmann's theorem tells us that we know there exists a square inscribed in each gamma n. So why don't we just sort of use compactness and try to take a limit of these squares as n goes to infinity, and in that way find a square that lies on gamma. So can we find a square like this? And the answer is maybe, but there is a potential problem, which is that if you look at these squares gamma n, there's nothing a priori to stop them from shrinking out to a point and giving you a sort of degenerate square where all four vertices coincide. Problem is, gamma n may shrink to a degenerate square lying on gamma, in which all vertices coincide. So that is a problem, and a priori there's nothing to suggest that problem doesn't occur. For example, we said not every cyclic quadrilateral inscribes in every triangle, but you can certainly approximate a triangle by a sequence of smooth Jordan curves that gets closer and closer to it. And each cyclic quadrilateral inscribes in each of those smooth Jordan curves. They just don't inscribe in the triangle. So what's happening is those cyclic quadrilaterals are shrinking out. But does it necessarily happen when the cyclic quadrilateral you're interested in is the square? All right. So we want quantitative invariance to obstruct shrink out. Okay, and this is where symplectic topology is going to enter the picture. So I'm going to build up a little symplectic picture for you all. So we're going to start with a Hamiltonian, which is just a smooth function on a symplectic manifold that we're interested in. And a symplectic manifold we're going to be interested in is C2. And what this function is basically just the square of the distance between the coordinates normalized by something. And then there's a associated Hamiltonian vector field, usually written xh, and this generates Hamiltonian diffeomorphisms. Even symplectomorphisms, which we'll call r theta. Which is just going to be the time theta flow of that Hamiltonian vector field. And how can we visualize this? Well, let me tell you. So here is a point inside C2. So that's just ordered pair of points inside C. So Z1 and Z2. And I've connected them by an arc. Okay, so that's a point inside C2. And I'm interested in what r theta does to Z1, Z2. Turns out what it does is you take them and you put a hinge at the midpoint and you rotate by an angle of theta. So this takes you to W1, W2, where that angle is theta. Okay. And so these Zi's and Wi's, these are vertices of what you might term a theta rectangle. So that's a particular similarity class of rectangle. It's the class of rectangle whose diagonals make an angle of theta with each other. So Zi, Wi are the vertices of a theta rectangle. In particular, if what you're interested in is squares, then you'll be interested in a pi/2 rectangle. But maybe we're just interested in all rectangles, and so then we're going to allow theta to vary. All right, brilliant. Now, what we're really about is when we can find an inscription of a theta rectangle inside a smooth Jordan curve gamma. Okay, and so that's going to be the case when Z1, W1, W2, and Z2 all lie inside gamma times gamma. So we're interested in Z1, Z2, W1, W2 being points inside gamma times gamma, then let's say you got an inscribed theta rectangle inside gamma, right? In other words, W1, W2 is in gamma times gamma intersect R theta gamma times gamma. So if you can find a point that's in gamma times gamma and in the image of gamma times gamma under this map R theta, then you'll have won the game, because you'll be looking at a point W1, W2 that lies in gamma times gamma, so endpoints lie in gamma. And it's also the image of a pair of points Z1 and Z2 that lie on gamma. Okay, so that's what's going on. Let me draw a geometric picture of this. So we're in C2, so I'm judiciously going to lose a dimension in this picture. So this whole thing is meant to be inside C2. This cylinder is meant to be part of gamma times gamma. I'll tell you what this plane is in a second. And then this is R theta gamma times gamma. And then what we're interested in is finding these intersection points between gamma times gamma and R theta gamma times gamma. All right, with some caveat, not all intersection points are going to be good for us. There's going to be a circle's worth of intersection points you can see here that we don't really care about. These are the degenerate inscribed theta rectangles, i.e. the ones where all four vertices coincide. So what's going on? This is a complex line. It's a diagonal. ZZ, points like that. And that intersects gamma times gamma and the rotation of gamma times gamma in this circle's worth of points. So that's just pairs of points ZZ as Z travels around the Jordan curve. Of course, if you take an arc of 0 length, ZZ, and rotate it, you just get back ZZ. So that's why you get this circle's worth of intersections here. So this is a circle here. This is ZZ. Where Z is in gamma. So what we're interested in is finding intersection points between gamma times gamma and R theta gamma times gamma that aren't these intersection points, this circle's worth of intersection points. Okay. Now, magic thing to notice is that gamma times gamma and R theta gamma times gamma are Lagrangian. Gamma is just a Lagrangian submanifold of C, and so gamma times gamma is a Lagrangian submanifold of C2. And this is, R theta is a Hamiltonian diffeomorphism, so it preserves things like Lagrangians. So these are both Lagrangian submanifolds of C2. And so figuring out when such things have intersection points is a question where there happen to be lots of tools that you can apply to arrive at an answer. In particular, so one thing you could do if you wanted to know that there are intersection points apart from this circle's worth is begin by smoothing away this circle of intersection points. You can do that because it turns out these Lagrangians intersect cleanly along this circle of intersections. If you smooth them away, well, it's like you've got these two tori, you cut them both along a circle and then you glued them together. So now you've got a torus that's like twice as long as the original torus that you started with. If you look at that torus, you'll see that it has minimum Maslov number 4. So it can't be embedded, so it must have extra intersection points. And so that's where one can apply this result of Polterovich-Viterbo, just conclude that there are extra intersection points. And that works for these theta rectangles, but there's also a way to make it work for general cyclic quadrilaterals. All right. But that's, like I said, that's not the game we're playing right now. We're trying to figure out if we can find big theta rectangles to preclude this shrinking out. Okay, so what we're going to do is do something slightly different, which is Floer homology. So figure out what I can erase. So we instead try to do Lagrangian Floer theory. That is, we set up a chain complex that we call Jordan-Floer chain complex. And it depends on this smooth Jordan curve gamma and this angle theta. And theta goes between pi and 0. And it's generated by intersection points between gamma times gamma and r theta gamma times gamma. But we want to take out this circle's worth of intersection points. The degenerate inscribed theta rectangles, and we try and make a Lagrangian Floer theory that has this as the set of generators. So this isn't, some sense which this isn't a very natural thing to do. The natural thing to do is to sort of keep this set of intersections around, but we're not really interested in this set of intersections, which is why we try and throw them out. So to sort of compensate for that, we also adjust the differentials. So the differential counts in the usual way pseudo-holomorphic strips. But we look at pseudo-holomorphic strips that avoid this this divisor, the diagonal. And so it's not obvious that such a construction works, that d squared squares to 0 and gives you a well-defined homology theory. But nevertheless, that turns out to work. And so then, if you could show, for example, that your homology is non-zero, that would tell you that there have to be inscribed theta rectangles, because the inscribed theta rectangles are exactly the things that generate this chain complex. All right, so let me tell you a bit about Jordan-Fleur chain complex. So JFC comes with an integer Maslov. You can read that as homological grading. And a real filtration known as the action filtration. And so both these things are inherited by the homology. The filtration gradings of the homology classes are called spectral invariants. So they're just going to be real numbers associated to each homology class, non-zero homology class, in the homology of this complex. And it's actually these things, these real numbers, that we're going to use to try and obstruct shrinking out. We'll see that in a second. So one question is, what is this? What's the homology of this chain complex? Does it depend on gamma? Does it depend on theta? The answer to both those questions is no, not up to isomorphism. So if you look at the limit as theta goes to 0 of JFC gamma theta, what this gives you is a sort of relative Morse complex of the Hamiltonian restricted to the Lagrangian. So this is the relative Morse complex of gamma times gamma with respect to h. So what I mean, this is gamma times gamma. It's a torus. And the function h, if you remember the function h, if you have 2 points in C, you just meant to take the a quarter of the square of the distance between them. So these points on the diagonal of gamma times gamma, which is point ZZ, h evaluates to 0 on those, otherwise h evaluates to something positive. This diagonal gets thrown out in the Jordan-Fleur complex, so it also gets thrown out in this Morse complex. I guess that's what I meant by relative. And so we're computing the Morse complex of everything apart from this diagonal. So we see that the homology Yes. So the homology turns out to be two-dimensional, and it's generated by a class in dimension 1 and a class in dimension 2. This is a statement about the limit as theta goes to 0, but there is ways of identifying the homologies for varying theta called continuation maps to standard tool in Floer homology. So the dimension of the homology is 2. So we get 2 spectral invariants. Li gamma theta for I equals 1 or 2, and those are just the filtration gradings associated to gamma 1 and the filtration grading associated to gamma 2. And is there a question about the use of the word gamma? I can see you itching. Maybe I should call these alpha. That one says gamma. All right. Okay. So that's great. So now we've got these numerical invariants, these real numbers, and the hope is that they're going to have something to do with the area or the size of an inscribed rectangle. And so then if we can find a lower bound on these spectral invariants, maybe that allows us to preclude shrinking out of these inscribed rectangles. So let me tell you what the action of an inscribed rectangle looks like. Okay. So here's an inscribed theta rectangle inside gamma times gamma. And the filtration grading of the corresponding chain group element is the sum of the shaded areas. Okay, and I recognize I haven't shaded any areas yet, so I'll do that now. So, so each inscribed rectangle is a generator of this chain complex we've been cooking up. And each generator of the chain complex has an associated real number called the action. Differential drops that action. So when you look at filtration grading of the homology, it's telling you something about the actions of the inscribed rectangles that generate the homology. So what are these shaded areas? So there's the yellow shaded area. Now, if that was the only shading I was going to do, would be in really good shape, because that shaded area tells you exactly about the size of this inscribed rectangle. Unfortunately, that's not exactly what the filtration grading is. It is extra areas. So we call that the double ice cream area. And so, of course, there's an ice cream pointing upwards and an ice cream pointing downwards. So this filtration grading clearly has something to do with the size of the inscribed rectangle, but not everything to do with the size of the inscribed rectangle because of these blobs. And so that holds us back from being able to prove theorem's as strong as we'd like to be able to prove. However, idea bound change in Li gamma as we vary gamma or theta, and hence preclude shrink out. So the idea is to just think about what we were doing with Schnirelmann. In some sense, you could try, if you're given a Jordan curve that you're interested in, you approximate it by a sequence of smooth Jordan curves. And you're going to figure out something about how quickly the associated spectral invariant is changing through that sequence. Then that might be able to tell you that the sequence of rectangles representing the homology itself isn't shrinking out. So that's the general idea. There's actually two variables that go into the spectral invariant, well, three if you count the I. There's the Jordan curve and the value theta. And we get different results by varying each one. In the interest of time, I'll just tell you the result that we get by varying theta. Okay, so varying theta. So suppose gamma is rectifiable. So more about that word later. Then there exists an interval which is a subset of the interval from 0 to pi, connected interval of length greater than or equal to the area of gamma divided by the radius of gamma squared. So I'll tell you what those exactly mean later, such that gamma inscribes every theta rectangle for theta in that interval. Not necessarily closed. Okay, so what's going on? All right, so you know what an interval means. I'm thinking of a connected interval. The area of gamma, I just mean the area of the region enclosed by gamma. The radius of gamma squared, well, you know what the diameter of a Jordan curve is. That's the maximal distance between 2 points. The radius, I just mean half of that. So it's half the diameter of gamma. So there exists an interval of this length such that gamma inscribes every theta rectangle for theta inside the interval. You'll notice that, say, a theta pi over 4 rectangle is the same thing as a 3 pi over 4 rectangle. So there's some redundancy going on there, if you like. Here's a, I should say maybe this is a theorem from last year, and a corollary is if the area of gamma is greater than pi times the radius of gamma squared over 2, then gamma inscribes a square. And the gamma is still rectifiable. And the reasoning is that if you do the math, you'll see that this gives you an interval of length bigger than pi over 2. And so that interval, however you stick it inside 0 pi, has got to contain the midpoint pi over 2, which is just a pi over 2 rectangle, which is a square. I said I was going to say a word about this rectifiability condition. Rectifiable, if you haven't come across it before, means essentially finite length. If you like, it's Jordan curves that you can approximate by a sequence of smooth Jordan curves where the lengths are uniformly bounded. And the reason for this condition is to overcome this problematic extra bit of the area that we have here. But it's kind of a technical condition. And the last thing I want to do is mention some very recent work of others. So this is Asano Ike from this year on the archive. And so they took our setup of these tori and this spectral invariant involving these actions, but they ported it into a different setting, which is a setting of microlocal sheaves, so not, it's kind of a different approach to the Lagrangian Floer theory. And we haven't, I confess, totally understood what it is extra that comes out of taking this different point of view. But the result that they claim is that if gamma is rectifiable with no hypotheses, then gamma inscribes every theta rectangle. Well, phrasing this correctly, theta goes between 0 and pi over 2. So every similarity class of rectangle is inscribed in every rectifiable curve. We haven't quite understood how that proof goes, but this seems to be the current state of the art. And thank you for your attention. I think I shall end there.
Very nice talk. Are there any questions?
You said at the beginning that any similarity class of a quadrilateral can be inscribed into a Jordan curve. But 4 points that are not closed as a circle can't be inscribed into S1.
Yes, I'm sorry if I phrased it a little in a confusing way. Yeah, I wrote down the statement of the theorem without all the hypotheses present at the start. The actual hypothesis is that the quadrilaterals that inscribe in every smooth Jordan curve are exactly the same ones that inscribe in the circle. If that makes sense.
Pardon, please. I'm not clear.
Yeah, that's yeah, I would have said that.
Any other questions?
He wrote down cyclic in the blank to solve the riddle. I don't have any particular questions as of now. So yeah, thanks for talk. Should we expect a statement that if you have an endpoint, just n tuple of points, they are embedded into any at least smooth German curve via a polynomial of some degree, n over 2 or n over 3?
Yes, so the precise statement that we believe to be true is that if you have 2 endpoints, then if you have 2 endpoints on the circle, so 2n cyclic 2n gon, then you can polynomially inscribe those into a smooth Jordan curve where the degree of the polynomial depends linearly on n. So when n equals 2, it's linear. When n equals, maybe it's affine linearly on n. N equals
n equals,
yeah.
I understand. But so far it's only proven for 6 points, right?
Yes. If we knew more about restrictions on so that came down to embeddability questions about Lagrangians inside C3, the 6-point question. The 8-point question comes down to embeddability questions about Lagrangians inside C4 and so on. And we don't have a good way to tackle those yet. We have sort of partial results when you have very particular configurations of 2 endpoints on the circle, which you make by taking a regular n-gon and then rotating it by an angle theta and taking the union of the points. Then we can use sort of Floer homology techniques to get the inscription results. But yeah, we believe that to be true. We also believe there are extensions to odd gons, odd cyclic gons, where the leading coefficient should be real and not complex. But we haven't figured out the right sort of symplectic or contact setup for those to be answered yet.
Thank you.
If we deform the Jordan curve, is there a statement about the way the inscribed shapes deform at the same time?
The way the inscribed shapes deform.
Yeah.
Well, I don't know if I would have a good answer to that question. I mean, we tend to take the inscribed shapes that we're interested in as sort of the constant thing. And so we'd deform the Jordan curve and ask about the moduli space of inscriptions of a particular point configuration rather than deforming the that point configuration. So I don't quite know how to approach what you suggest.
Okay.
You previously mentioned that embedded Lagrangian tori in C2 has a minimum mass Lorentz 2. So maybe I missed it. So where do you use this? Or why are you mentioning that?
Well, so we didn't use this in this discussion and this setup of this Floer homology. However, if what one was interested in was just whether there are inscribed theta rectangles, then a shortcut to get that answer is to avoid setting up the Floer homology and just to smooth away this circle of intersections. Then you'll get an embedded, then you'll get immersed Lagrangian torus whose intersection points correspond to, self-intersection points correspond to inscribed theta rectangles. And so if you know that that Lagrangian torus is not embedded, then it does have self-intersection points, so therefore there exist inscribed theta rectangles. So it's sort of a shortcut to get that answer. But also, that idea can be used to prove not just things about theta rectangles, but cyclic quadrilaterals. And I didn't give the full setup of that story.
Let's Franco speak again.